One information, this is our 60th session, proudly brought to you by the Faculty of Engineering, University Technology Malaysia, UTM. By the way, I'm Jay Suman from the School of Biomedical Engineering and Health Sciences, UTM. And before we proceed any further, please spare some time, ladies and gentlemen, please spare some time to click the like button, on our Facebook page. Okay, you can find the like button right just below our video right now. Okay, please click the like button on our Facebook page and like this video as well, this live video. I would just like to double confirm if my voice is clear and loud. Okay, and also please help us to share and spread the news of this event, and hopefully more people can benefit from this session. Okay, ladies and gentlemen, our distinguished speaker of the day is Professor Wuqiang Yang. Yeah, our distinguished speaker of the day is Professor Wuqiang Yang, and he is a prominent scientist in the same field as me, tomography. So I have personally benefited a lot from his massive publications and his great work in this field, especially during my master's and PhD studies. Even in my career right now, we still, me and my team, we pretty much benefit a lot from his publications as references and also citations, and even also collaborations as well. So, so without further ado, also, should you have any question during this webinar, please post it at the comment section, and our team will assist you during the Q&A session. So I don't want to be the spoiler here. I'm going to let our Dean, Faculty of Engineering, University of Technology Malaysia, Professor Dr. Engineer Muhammad Rafiq bin Dato' Abdul Qadir, to deliver his welcoming speech and further introduce our speaker. Welcome, Prof.
Thank you, Prof. Thank you, Dr. Jai Suman, for chairing the session. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to our 60th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Professor Wuqiang Yang from University of Manchester, United Kingdom. A bit about our distinguished speaker today. Wuqiang Yang is a Fellow of the IEEE, Fellow of the IET, and Fellow of the Institute of Measurement and Control. Since 1991, he has been working with UMIST, now University of Manchester in the United Kingdom, and became Professor of Electronic Instrumentation in the Department of Electrical and Electronic Engineering in 2005. He has published more than 400 papers. He is an Associate Editor of the IEEE Transaction IM, editorial board member of 6 other journals, including Measurement Science and Technology, and an IEEE Distinguished Lecturer. So that is a brief biography of our distinguished speaker today. Here now is Professor Wuqiang Yang from University of Manchester, United Kingdom, to talk on the electrical capacitance tomography and its industrial applications. Professor Wuqiang Yang, over to you.
Thank you very much. Thank you. So now I can share my screen. Is a share screen. Today, I talk about electrical capacitance tomography and industrial applications. As the Dean and another professor introduced, I'm Wuqiang Yang from University of Manchester in the UK. Today, I have 5 sections: Introduction, Principle of ECT, ACbased ECT System, Industrial Applications, and a short summary. Let's start from a short introduction. At first, I'd like to spend 1 or 2 minutes talk about Manchester. I believe many of you knows Manchester because of 2 football clubs, Manchester United and Manchester City, rather than 2 industrial revolutions. UMIST has almost 200 years history. UMIST was established in 1824. In 4 years' time, UMIST will be 200 years old. Now, we are merged by University of Manchester. Now, this university is very big, 39,000 students. We do have 25 Nobel Prize winners, some famous people like Alan Turing, Reynolds, Roosevelt, and ARM inventor, Steve Ferber. We work together closely. Now, we because of one of the Nobel Prize winners in graphene, the UK government gave us a few hundred million pounds money to establish 2 centers. One is for fundamental research, the other one is for commercialization. Last year, University of Manchester just finished another new building. It's a material, 315 million pounds. We are moving to this new building. This is called Manchester Engineering Campus Development. Actually, nobody tried to remember this name. Basically, university tried to integrate all engineering department together into this building. Personally, I don't like this building because there will be no individual offices. All academics seats almost one roof. Now, still we don't know is a shared office or is under one roof. At least, university has confirmed no individual offices. That is, I would say, this is a disaster for academics. Now, we talk about sensing. Actually, it is application that determine what materials we should deal with. And then we should consider what property of the material we deal with. It is the material property that determine the sensing modality. But this picture, we can summarize the frequency range from high frequency to low frequency. You can see from high frequency to low frequency. Our ECT work around here is a few hundred kilohertz, less than 1 megahertz. That is frequency range for ECT. If you don't remember what ECT is electrical capacitance tomography. Now, the principle of ECT is not difficult. I can try to summarize the principle of ECT by 3 bullet points. The first one, ECT is based on capacitance measurement. We use this type of sensor. We have electrode around a process so that we try to get information from inside. Now, by this sensor, we take measurements of a process from many different angles by different electrode combination. We try to reconstruct permittivity distribution inside or in this imaging area. We start from a sensor. Here I show you 2 extreme sensors. One is a high pressure sensor. We designed this sensor. Actually, Schlumberger made this sensor, the left one, this one. This one is a high pressure sensor used for oil industry. It's up to 10 megapascal, which is 100 bar pressure. This sensor used for gas oil water flow measurement. I believe in Malaysia, the gas oil industry play important role in economy. So this work should be relevant to Malaysia. Actually, I visited Petronas at least twice. Petronas company. Also, I visited Petronas University. Hopefully, we can have some type of collaboration with Malaysia in this area. Later on, we'll talk about more about gas oil water flow measurement. On the right, this is a high temperature sensor. I work with Chinese Academy of Science. They have a big project to convert coal into gas, into oil, and then into plastics. This is a bigger project. For this project, they need to deal with the high temperature. This sensor can deal with 1,000 degrees. This is a very high temperature. MGO, this is a methanol to olefin. That is their work. For sensor, I published a paper in 2010. Now this paper has been cited 340 times. Now with the ECT, what we can get on top row, this is a typical distribution. You have one object, two objects, and one ring, and central you have another project. Our objective is to reconstruct the image to show the distribution like this. Those pictures I took perhaps 20 years ago by normal camera, by film camera. But the principle is the same. Also now we can obtain much high resolution image, but the principle is the same. I keep those pictures to show the principle and also to show the history. Now from an ECT image, what we can get? Obviously, we can see the distribution. That is in oil industry, in industry, they call the flow regime, such as stratified flow or cone flow or annual flow. By integrate pixels together, we can derive the concentration of a certain material. For example, pulverized coal in power station pipes, or catalysts in petroleum FCC. We can use twin ECT sensors to get a signal from both sensors, and then by cross correlation, we can try to derive the flow velocity profile. That is actually one PhD project I just set up for a PhD student, because this work is required by Ph.D. in USA. So far, still in industry, some processes it's difficult to measure. If you can't measure, certainly you can't control. So if by tomography we can change non-measurable process into measurable process, and then we can control process. There are many different tomography modalities. Depends on what sensing principle you use. ECT has many advantages over other modalities, such as no radiation, non-intrusive, non-invasive. The speed is fast. The sensor size is flexible. I give two figures here, 8 millimeter and 1 meter. Those are two extreme diameters I did. ECT sensor is robust, can withstand high temperature, high pressure, and also the ECT system is of low cost. Now to develop ECT system, we do have some challenges. So in hardware, the capacitance value is very small. Normally, we deal with picofarads. With ECT, we have to deal with the femtofarads, which is 1,000 times smaller than picofarad. If I give you a more exactly figure, that is 0.01 femtofarad, that is 1 times 10 to minus 5 picofarad. That is a very small capacitance we have to deal with. We need high speed so that we can show real-time image. we need a high signal to noise ratio, at least 60 dB. 60 dB presents 1000, that is 0.1%. In mathematics, we have to deal with nonlinear relationship between capacitance and permittivity. To reconstruct the image, we need to inverse a matrix. We need to solve permittivity distribution from a capacitance measurement. That is an underdetermined solution because the number of measurements is limited. To inverse the matrix, we have to deal with year pose, year condition, inverse problem. For engineering, I have listed the following challenge. The diameter. Some users ask, can you do much smaller? Can you do much bigger diameter, such as much larger than 1 meter in diameter, down to micrometer in diameter? Now, for ECT to be used in real industry, we have to re-engineering ECT sensors, not only high temperature, high pressure, but others like intrinsic safety, explosive proof, and attacks. For example, if we intend to use ECT in oil industry, in particular in gas industry, we have to get attacks certificate. We have done a lot of work with the pharmaceutical industry. One difficulty with the pharmaceutical industry is the pharmaceutical regulations very strict. It is difficult to meet those regulations. The last one is the cost. Recently, a company in South Korea asked me, can you drop your price to a few hundred US dollar rather than a few like 10,000, 20,000, that range? That is another difficulty. Is that if you can drop the price to 300 US dollar, I can place thousands ECT systems in semiconductor industry. Once we have capacitance measurements, how can we get image? That is called image reconstruction. Let's assume we can get capacitance measurement. We can deal with a small capacitance measurement. From a 12 electrode sensor, we can get 66 independent capacitance measurements. If we divide this area into many small pixels, we try to determine or to guess what's the permittivity value in each pixel. So if we can do this, that is image reconstruction. So the task of image reconstruction actually is assign permittivity value to each pixel here. Each pixel according to measured capacitance on this side, i.e. to solve inverse problem, which is commonly called image reconstruction. There are many image reconstruction algorithms. Basically, there are two groups. One is a single step, the other one is iterative. Now, with the single step, the typical one is a linear back projection. And that is this equation. There are many other different types. And this is another typical one called the Tikhonov. Actually, it's not difficult to derive Tikhonov equation, but it's difficult to use because here you have a relaxation factor that is difficult to decide. Another bigger group of algorithm is iterative. There are many different types, like a NewtonRaphson, like a Landweber. Also, many times exist only Landweber is popular. I can see almost all researchers working on tomography use Landweber. In 1999, I published the first paper, Landweber algorithm. Actually, there is nothing related to Landweber. I derived this equation here. This equation, I derived this equation based on my control knowledge. For undergraduate, I studied instrumentation and control. I studied process control. Based on my control knowledge, I derived this equation. Before I published a paper, someone from Leeds University told me, oh, this equation is very similar to Landweber equation. You can call this equation as a Landweber. So I called, in the first paper, I called this equation as a Landweber algorithm. So since then, all people over the world know this equation is a Landweber iteration. Actually, in the first paper, if I call this equation is a Yang iteration, now in the whole world, they know this is a Yang iteration. This is the biggest mistake in my academic life. There are some other iterative algorithms. I don't have to remember all. 2003, I published a paper on image reconstruction algorithms for ECT. This paper so far has been cited 1,155 times. Those two slides, I wouldn't intend to explain those two slides. I just like to let you know, I use those two slides to teach our MSc student where this NewtonRaphson equation come from. It looks quite frightening. Look, this equation actually is not that difficult. By those two pages, from my engineering mathematics background, I can derive this equation. So it's not too difficult to derive. Now, part 3 about ACbased ECT system. This picture here shows you our ECT system. We call it ACbased ECT system because this hardware is based on AC circuits. I designed this circuit by myself. Actually, this box, I made this box by myself. There are 16 channels in parallel to achieve speed. The speed of this system up to 300 frames per second. The signal to noise ratio, if you remember, I talked about signal to noise ratio. I said for an instrument, we need 60 dB signal to noise ratio. With this instrument, the signal to noise ratio is actually 73 dB. I tested many times. It is consistent. It can operate with twin plane sensor so that we can implement cross correlation velocity measurement. The interface is real time. By the way, many people use USB as an interface. With the USB, you can never achieve real time. Only PCI or PCMCIA you can achieve real time. This interface is user friendly. You don't have to read instruction manual. You can operate this system. Some latest developments. We have anti-electrostatics. This is important for gas-solid flow measurements, in particular in dry region, such as in Beijing. If you during summer, if you try to operate gas-solid flow, you can see sparks because of electrostatics. I guess this is not a serious issue in Malaysia because it is more moisture. We have a remote control so that we can control ECT system 300 away from the instrument. On hardware, I published a paper in 1999. This paper's citation is not very high, 340 citations. So that is the latest development, a real-time 3D imaging. Later on, I show you how this works. This AC-based ECT system has been used by many bigger companies. I show you those users. such as I'm quite proud of this. The Rolls-Royce, they use my system. They have a permanent setup in W. I don't know if every engine they test. I know what exactly they do, but they wouldn't let me involve because it's their secret. And also a big name like NASA. Currently, we have a joint proposal with NASA. Other big names here. Let's talk about industrial applications. The first one is gas oil water flow measurements. I worked with Schlumberger for many years. Currently, we have a joint project. They intend to develop a very fast tomography system. Here is to show previous work. We had a big project. We work with Schlumberger and NEL, National Engineering Lab, together. We use ECT to measure oil continuous flow. We use a microwave impedance to measure water continuous flow. We use microwave Doppler to measure liquid velocity. Use a Venturi to measure pressure difference. Use ultrasonic to measure thickness of a liquid ring. This picture here shows a test in National Engineering Lab. That is a sensor and assembly here. Here is the ECT sensor there. I have that is a microwave Doppler, and here is a microwave thick one. This is ultrasonic. This is assembly about 1 meter long, less than 1 meter long, about 50, 60 centimeters long. This they called spool piece. So because we make the flow swirling, we can generate distribution like this. I have all liquid. I have some gas, more gas, and more gas. Now we can get distribution. Now from a historical record, we can get this type of image. That is a time record. Here you can see this gas core in the center because of a swirling effect. You have a liquid on top and in bottom. Actually is around. That is a vertical flow. With a vertical flow, we don't use swirling. You have a piece of liquid, piece of gas. Another application is pharmaceutical flow despite. We work with AstraZeneca in Sweden and GA in the UK. To make a tablet, there are 4 processes in the end: granulation, drying, compression, and coating. 3 of them involves flow despite. I'll show you here. The problem in industry is flow despite still like a black box. They have to trial and error. The consequence is less efficiency, long time, more energy consumed, more pollution, and more importantly, is product quality cannot be guaranteed. By ECT, we can provide the image in real time of gas-solid distribution, moisture distribution, and dynamic process. We tested on different scale flow despite. And see, this is a small scale, this 20 centimeters in diameter. This is a middle scale, this is a large scale. This is a 1 meter in diameter, production scale. Actually, we did experiment here with this facility in Sweden, Bubendorf. Now here is one result, a typical application is the drying process. With the moisture measurement, one curve, this black one, this is by moisture meter. Moisture meter, we can take a measurement offline. The right one, this is the online ECT measurement. You can see this is a good agreement together. In the end, agreement within 0.1%. That is, I show you more applications. One here is an aircraft fuel supply. This is a test for Airbus A380. So I can't tell you exactly what they worry. If I tell you, you start to worry when you take an aircraft. Actually, it is dangerous to take an aircraft in physics. That is ECT, our ECT system we use to measure fuel supply. Here is another piece of work on wet gas separator. We work with Shell in the Netherlands. This work is to image here. Here, that is a separator. I believe this separator now operating in Malaysia. This is quite long, about 5 meters long. And here is a separator. The basic principle is a cyclone principle to swirl, make this flow swirling so that liquid on wall and the gas in center. And here is a separator to get the liquid out. So that is the image we generated by our tomography system, so that you can see this the liquid there, liquid there, liquid there, liquid there. Another example is gas-solid flow measurements. This work actually with Honeywell in USA. I went to Chicago. I worked with them together. This facility there is to implement FCC. Basically, it's oil cracking to get petrol, to get diesel. But this process is never optimized because they can't measure accurately gas-solid flow. That one, here is another example, is a cyclone separator. I work with Chinese Academy of Science on circulating fluid beds for coal combustion. I don't know. I guess coal combustion is not important in Malaysia because in Malaysia you have a lot of oil. Oh, now I can summarize. I can see now it's 33 minutes. I can summarize the talk. After this summary, I show you how a tomography system works. I have another screen. I can share another screen. My summary, ECT is the most mature to compare with other industrial tomography modalities. It is suitable for multi-phase flow measurements. It is a useful tool for understanding complicated processes in industry, verify CFD models and simulations. I can talk about a little bit more about this. Many people do simulation. They have CFD models. Now, how you can verify simulation results? ECT is a good tool. It is useful for measurement for control, in particular for those processes currently can't be measured. ECT has been used in gas oil industry, pharmaceutical industry, power industry, and other industries like clean energy. ECT can make unmeasurable industrial process be measurable and hence controllable. I can think of two important future developments. One is multi-modality. ECT itself can deal with the dielectric process. In some cases, we have to deal with not only dielectric process, but involve, for example, conductivity. Now, in that case, we can combine ECT and electrical resistance tomography together, or we can combine ECT with microwave resonance cavity sensor together. I have a student in Malaysia, a former student. Her Ph.D. work is about microwave resonance cavity sensor. In future, we may work together how to combine ECT and microwave resonance cavity. Another big topic is post-processing. So far, little work has been done on post-processing of ECT data. In future, we can consider how to make use of those fancy or popular phrases like big data, deep learning, AI. This could be good PhD work. Thank you very much for your contribution. I think time about right. Now I stop my talking. I like to share another screen so that you can see how a tomography system works. Can you see a second screen? Okay, now you can see a second screen. I have a sensor. You can't see this sensor. I can have a sensor in my hand. If I empty this sensor, you can see this is an empty space. If I turn the sensor around, let plastic beads fill the sensor, you can see this is a full screen. If the beads fill some part, like if I try to fill half, I try to let the screen halfway. Okay. If I fill some part, you can see this where is the beads, where is air. All right. I talk about real-time 3D imaging. If I change to 3D, you can see where is beads, where is air. If I have beads flowing, you can see this 3D image. If I wave this sensor, you can see this wave. You can see this wave. Now this is a real-time demonstration how we can generate 3D image. Okay, I think I stop here. I stop screen sharing so that we can you can ask a question. We can have a discussion. Shall I stop? I stop sharing now. Okay, I think I finished my talk and my demonstration. It's about the right time. 40 minutes.
Thank you very much, Prof, for the wonderful presentation. I was enjoying the live demonstration. That was real time, right? That was real time.
Yes. Yeah.
Okay, Prof. So maybe it's time we can pick up some questions from the crowd. So ladies and gentlemen, our viewers, yes, we have, if you have any question, please post at the comment section, and then our support team will display your question as much as we can to cover it at this short session. So we have a question by Yasmin Abdul Wahab. For information, Prof. Wuqiang, Dr. Yasmin Abdul Wahab is one of the, one of the researchers in the tomography field as well in Malaysia. So she's asking the question, how does ECT apply for steel pipes? Is it based on invasive approach? Yeah, would you like to respond, Prof? Please.
Okay. When I show you two extreme sensors, one is for oil industry, one is for clean coal application. Those two sensors actually are steel because of a high pressure, high temperature. In particular, high pressure is steel. But with the steel, we have to use internal insulation layer. You need an insulation layer such as PEEK is a good material. We have made several this type of sensor. Yeah, of course, in principle, you can't have a capacitance sensor just outside of a steel pipe. You have to put electrodes inside. You make your sensor so that you can like a sandwich in a steel pipeline. Basically, you need the insulation layer, put the electrode inside. But we know how to do it. In engineering, it's doable.
All right, so it is invasive. It has to be invasive approach. Yeah, right, Prof. Huh? So yes, Yasmin Abdul Wahab, I'm sure you have some extension question from this question. You may contact Professor Wuqiang for further explanation later afterwards. We will take the next question, please, from the crowd, from Muhammad Afifi Abdul.
You can use the chat. Or they can use the chat. Yeah, I can see chat.
Yeah. There's a chat over there. By the way, Prof, the question is displayed on the screen, as you can see on the screen right now.
I can see. Can ECT be used in measuring ppm of solid in exhaust gas? In another case, in the flow of water from dam to hydrocarbon. Okay, that's for application. I showed you white gas separation. White gas application actually is a ppm, about 60 or around 50, 60 ppm. It's a very small percentage of liquid. We did manage to image white gas, but it's not easy to do it. You may ask me why we can do this. The most reason is white gas separation. The flow is very, very stable. It wouldn't change quickly. So we need a much longer time to take measurements so that we can manage such lean flow, like down to ppm. If we talk about exhaust gas, I guess we can't do it because with the exhaust gas, the solid is not stable. You can change too quickly, so you need a very fast measurement. Now, in that case, it is difficult to deal with such low concentration. That is my answer.
Well, great. Okay. Do we have any other questions? There's one from my colleague, Prof. Wuqiang. The question is, ECT, you have mentioned ECT in pharmaceutical usage. So to what extent ECT has been applied for other medical lines?
For other medical, recently we published a book. One chapter is electrical tomography for medical applications. This book now is available, just available. It's from IET Publishing. The book, actually in my introduction, I mentioned this book, this imaging sensor technologies and application. If you are interested, you can read this book. You can read this chapter about the medical application. Overall, my opinion is it is difficult. People did try to use ECT for medical applications. It is difficult.
Okay then. Okay, so for those who asked the question, you can refer to the book by IET Publishing, Electrical Tomography for Medical Applications. Yeah?
No, the book name is Imaging Sensor Technologies and Applications.
Imaging Sensor Technologies and Applications. Okay, great. Okay, the next question, I think we still have time for the last question. Okay, so Prof. Wuqiang, how do you see the field of tomography during the imaging of fourth industrial revolution? So it's pretty much related to 4IR. How do you see the field of tomography during the imaging of fourth industrial revolution? So Yeah. What's your opinion, Prof?
What is for?
Yeah, fourth industrial revolution. So, you know, we have the first, second, third, and now it's the fourth revolution of industrial. Yeah.
There is no clear definition. What is the third? What is the fourth? The first one, second one is clear. The first one is textile industrial revolution. The second one is the engine industrial revolution. The third one, which one is the third one? Maybe computer, maybe information. The fourth one, some people may say is AI. We don't know.
Yeah.
But for future application, I think the most bottleneck is the cost. If we can, as I said during my talk, if we can reduce the cost to something like $1,000 US, $2,000 US, that we can have many applications of ECT. This is not a technical problem. It's economic problem. It's a business problem.
Well, Prof, talking about economy, how do you see that if we miniaturize all these things, you know, in terms of sensors and everything, and we are talking about nanotechnology, this kind of stuff? So what do you think, moving tomography towards miniaturization?
I think it is prospective, promising. Because if we can really miniaturize, even integrate, I heard the cost can be 1%, a few percent, can be a few percent, somewhere between 1% and 5%, can be much lower than what is the cost now. If we use individual components, even individual components itself, the cost is much higher than integrated version. If someone is willing to invest to make like a IC, we can make a IC, ECT IC. Now it is possible to have a very low cost so that we can massive application. It is possible.
Okay. Well, that is some promising future applications and development as well. Yeah. So, okay, well, Professor Wuqiang, I think we have pretty much covered some of the awesome questions, and we have some awesome feedback from you. But due to time constraint, I'm afraid we have to end our Q&A session. So before we end the whole session, Prof. Wuqiang, would you like to give a closing remark, or maybe just a short conclusion before we end this session?
Okay. It is my pleasure to talk to you via this type of a platform. This very, I feel very strange. If I talk to you face to face, I can see many students. That is, I would feel more comfortable. But with this, still I feel I'm talking to a screen. But it's okay. I can manage. It is my actually I work with Tsinghua University College for many years. I visited Tsinghua University College many times. Still now it's due. I need to visit Kuala Lumpur again because of the spreading of virus. I can't travel at all. I hope in the near future I can have a chance to visit you, to visit the University Technology in Malaysia, so that we can meet face to face. We may find collaboration opportunity with such as Petronas oil company. With if we can find other applications, I don't know, maybe like palm oil. I don't know. So what type of collaboration we can find? If we can identify opportunity, I hope we have opportunity to collaborate, because time to time I can see a call for proposals for collaboration with Malaysia.
That's great. That's great, Prof. We are so looking forward for that collaboration, and hopefully after the pandemic we can arrange some
meetups
and a physical meetup, I mean.
Yeah. I'd like to thank all audience, all students. It's encouragement. Like, as I said, I feel quite strange like this type of talk. I hope the student can get something from my talk.
Okay, Prof. So it's been a pleasure for me to share the virtual stage with you, although it feels awkward. Anyway, thank you very much for your wonderful insights of electrical capacitance tomography for industrial application. And for hopefully we can meet up soon again. So with that, we will end this session. Thank you very much, Prof. Thank you, everyone. Ladies and gentlemen, thanks all. Bye.
Thank you. Thank you. Bye. Bye-bye.